Example number 1, solve the differential equation using Laplace transform, that is d squared y over dx squared plus 5 dy over dx plus 4y is equals to 0. Given that when x is 0, y is 0 and dy over dx is 1. Now what this implies that when they say when x is 0, y is 0, and you know very well that, so we want to use Laplace transforms. So in Laplace transform, if you have y to be a function of x, then y a function of x is expressed in that manner, because we said a function can be denoted by any letter, isn't it? So this is y being a function of x. So when you say when x is 0, y is 0, it simply implies when x is 0, y is 0. Meaning while there is x, you put 0. So when you are given y of 0 to be equals to 0, it simply means y is 0 when x is 0. Are you seeing the implication? Then in this other one, when you have dy over dx is equals to 1, then you know that is the derivative y. Y is a function of x, meaning if you differentiate y, is the y prime of x, isn't it? Are we together? So they will write it to you as y prime of 0, y prime of 0 is equals to 1, meaning they are telling you that when x is 0, the derivative of y is what? When x is 0, the derivative of y is 1. So I'm showing you another way of denoting this initial or boundary conditions. Are you seeing that? This is another way of denoting this initial or boundary conditions. So when you go to Laplace transform, you know that the Laplace transform of a function f of t is given by the integral from 0 to infinity of exponential negative st ds. The negative exponential st dt. So if you differentiate this, it is negative a function f of t. Where is our f of t? It is given by the Laplace transform. This function f of t is f of t exponential negative st dt. It is the function when we are differentiating a function, when we are integrating a function f of t, it is with respect to t. Are you seeing that? Exponential negative st. So from there, if you want the first one, if you want the Laplace transform of exponential at, the Laplace transform of exponential at, if you substitute it in this equation, you get 1 over s minus a. If you want the Laplace transform of t raised to power n, then it will be n factorial over sn plus 1. That implies that when you have Laplace transform of a constant 1, then it will be what? It will be 0 factorial over s0 plus 1, because your n is 0. Laplace transform of 1 once means t raised to power 0, meaning our n is 0. Are you seeing that? So you end up with 0 factorial is 1 over s. So it means when you are looking for the Laplace transform of t, then it is raised to power 1, meaning it is going to be 1 factorial over s squared. 1 factorial is just 1. S squared is 1 plus 1, n plus 1, isn't it? If you are looking for the Laplace transform of, we have dealt with the exponential function of cos at. The Laplace transform of cos at is given as s over s squared plus a squared. If you do that integration, the Laplace transform of sin at is given by a over s squared plus a squared. The Laplace transform of exponential at cos wt is given by s minus a over s minus a squared plus w squared. If you're looking for the Laplace transform of exponential at sin wt, then this is given by w over s minus a squared plus w squared.
Yes.
If you do this integration, we go on if you're looking for the Laplace transform of the first derivative dy over dt, then you get as Laplace transform of y minus y of 0. When you are looking for the Laplace transform of d squared y over dt squared, then you will get, when you're doing those integrations, you will find they're actually integration by parts. If you can do that, you will get s squared, the Laplace transform of y, minus s, the Laplace transform of y of 0 minus y prime of 0. If you're looking for the Laplace transform, for instance, of t raised to power n and f of t, then that is just going to be negative 1 raised to power n, e raised to power n over ds raised to power n of the Laplace transform of f of t. So, there are very many cases of Laplace transform, and they are just integration by parts. Now, how are we going to use the Laplace transform to solve this second order, homogeneous ODE? We now want to use the Laplace transforms to solve this second order, homogeneous ordinary differential equation. So what we do here, we have our equation is this. For you to use Laplace transform, meaning you introduce Laplace in each and every term, isn't it? So we are going to get the Laplace transform of, the first term is this, that is the Laplace transform of d squared y over dx squared, then plus 5, the 5 is a constant, you factor out, so it is 5 Laplace transform of dy over dx, then it is plus 4 Laplace transform of y, then Laplace transform of 0, that is just 0, isn't it? Yes. So from here, you start the substitution. What is the Laplace transform of d squared y over dx squared? We found that is s squared Laplace transform of y minus s, y of 0 minus y prime of 0. Then it is plus 5. Then what is the Laplace transform of dy over dx? That is going to be s Laplace transform of y minus y of 0. Then it is plus 4 Laplace transform of y to be equals to 0. Start the substitution. You can see y of 0 is 0. Meaning where there is y of 0, you put 0. Y prime of 0 is 1. Where you have y prime of 0, you put 1. So it means this one automatically goes to 0. This is 1. So if you substitute, you get s squared Laplace transform of y, this is 0 minus y prime of 0 you found is 1 minus 1. Go on, open that bracket. 5 times s is 5s. So it is plus 5s Laplace transform of y. 5 times y of 0 is 0. Y of 0 is 0 from top there. So we are done with that. Then we go here. Plus 4 Laplace transform of y to be equals to 0. So the next thing, you collect the Laplace transform of y, you put them together. Meaning this minus 1 goes on the other side of the equation, isn't it? Yes. You are collecting the like term. So what are the coefficients of Laplace transform of y? What are its coefficients? The first coefficient is s squared. That is the next coefficient is plus 5 plus 5s. Then the next coefficient of Laplace of y is plus 4. So all those are coefficient of Laplace transform of y to be equals to 1. Because this negative 1 going on the other side of the equation, it becomes positive 1. So we divide both sides with the coefficient of this. We divide both sides of the equation by x squared plus 5s plus 4. Divide both sides by s squared plus 5s plus 4. So this goes with this. You remain with the Laplace transform of y is 1 over s squared plus 5s plus 4. This is quadratic, so you want to use the method of partial fraction. So first of all, can you use factorization? Can factorization do this? A product of 4 and the sum of positive 5. That is 1, positive 1 and positive 4, isn't it? Yeah. So it means it is going to be 1 over s squared plus 4s plus s, isn't it? It is going to be maybe s squared plus s plus 4s plus 4. Isn't it? Factorization. So that is going to be 1 over, if you deal with it, s is a common factor here, positive 4 is a common factor here. So it means it is s plus 4 into s plus 1. S times s squared. A times 1 is s, 4s, you get a total of 5s, 4 times 1. See, this is what you have. Yes. Those are algebra, things you did in class 4, so you just use that to deal with it. Then, you go to partial fraction. So you want to resolve this into partial fraction because it is a product. This is a linear factor, this is a linear factor, isn't it? Yes. So resolving linear factor into partial fraction, it is a over s plus 4. You are done with the first linear factor. Then it is plus b over s plus 1, isn't it? Yes. You are resolving because this one is also a linear factor. You see, those ones were now just passing through because there are things we dealt with, isn't it? You're just passing through. So after that, we now get the LCM here is s plus 4, s plus 1. So s plus 4 goes here how many times? S plus 1 times. So we have as plus 1, then plus s plus 1 goes here how many times? S plus 4. So we have b into s plus. Then this side of the equation we have what? So we have 1. Over s plus 4 over s plus 4 s plus 1. So the denominator is the same. It means we are comparing the numerator, isn't it? Yes. We are comparing that the numerator. So if you compare the numerator, start comparing. If you open this, what do you get? This side we have 1 is equals to a into s plus 1, then it is plus b into s plus 4. Are we together? Are we together? So you are comparing the constant term on their own and the terms of s on their own, isn't it? So can you collect the terms here? So a, what are the coefficients of s here? It is as and bs, isn't it? So a times s, you get as, then plus b times s, you get bs. So it is a plus b to s, isn't it? Yes. You've collected that one, you go to the constant term. A times 1, it is plus, a times 1 is just a, then you've collected that, b times positive 4, positive b times positive 4, plus 4b. So have you seen you've collected the terms of s together and the constant terms together, isn't it? Yes. To be equals to 1. So you compare the constant term, which is a plus 4b, is equals to the constant term this side, which is 1. The term for s, the coefficient of s, which is a plus b, is equals to the coefficient of s this side, which is 0. Because there is no s this side, meaning it is 0, s plus 1. So the coefficient of s here is 0, the coefficient of s there is a plus b, isn't it? Yes. Are we together? So see, solving this is now very simple. Yes. Meaning, when a is equals to negative b, if you take b the other side, isn't it? Yes. So where there is a, you put negative b. So negative b plus 4b, you get 3b to be equals to 1. So that implies b is 1 over 3. So if b is 1 over 3, it implies a is what? Negative b. Negative 1 over 3. Are we together? Are we together? Yes. Good. Now, having done that, the next thing is now to take them back to your equation. What was your equation? The Laplace transform of y was what? Was 1 over this, which we've transformed to be a over s plus 4. Are you seeing? A over s plus 4, a is negative 1 over 3 into s plus 4, meaning 1 over s plus 4. Then it is plus b over s plus 1, meaning plus b plus 1 over 3. S plus 1 is the same as 1 over s plus 1. If you factorize out a and b from the bracket, isn't it? Yes. Are we together? So what do you see inside here? For you to get y, when you take Laplace the other side, it becomes the Laplace inverse. So it means y is now going to be negative a third Laplace inverse of 1 over s plus 4, then plus a third Laplace inverse of 1 over s plus 1. If you've done that, you can now see, these are now just to be seen. 1 over s minus a, that is a Laplace transform of exponential at. You can remember the Laplace transform of exponential at is 1 over s minus a. Meaning, if you get here, this is y is negative 1 over 3, 1 over s plus 4. S plus 4 means it is s minus negative 4. So it is 1 over s minus a. Meaning our a is negative. Negative 4. So it means this is going to be exponential negative 4. In our case it is not t, in our case it is x. So this Laplace transform is from ax, because our t in this case it is with respect to x not t, isn't it? So it is going to be negative 4 exponential x. Then we go to the next one. This is 1 over s minus a, meaning plus 1 is simply minus negative 1, because it's supposed to be s minus a. Here we were differentiating with respect to x, not t, meaning where there is t we put x, isn't it? Yes. Meaning the Laplace transform of this, if you take Laplace the other side, meaning you get exponential ax, is Laplace inverse of 1 over s minus a. So the Laplace inverse of 1 over s minus a, our a is negative 1. So that is going to be plus a third exponential ax, but our a is negative 1, so exponential minus x. So you found the solution of the second order homogeneous ODE using the Laplace
equation
transform.